And now we are going to see another application of the Vertex equation. Vertex equation is used to develop the fundamental theorems. As you know that similar to the elastic analysis, the correct elastic solution must satisfy three conditions as follow. The first condition is equilibrium condition. And the second is mechanisms condition. Okay, mechanism condition. And the last condition is moment condition. Let's say MP smaller than MP, M smaller than MP. Moment should be always smaller than MP. The moment, plastic moment capacity of the section. Problem is that these three conditions can be satisfied easily for a simple structure. But for a complex structure, it is not easy to satisfy all of three conditions at the same time. Okay, so that's why we need an approximate solution. Okay, we need an approximate solution. So by using the Vertex, we can develop different theorems for plastic solution. Okay. In order to judge the accuracy of the approximate solution, and seven general principles and basic plastic theorems are established as follows. Then I'm going to show you very briefly on different theorems that you can use in plastic analysis and design. The first one is uniqueness theorems. Beyond these uniqueness theorems, they use the three different conditions: mechanism condition and equilibrium condition and the moment condition. Then they determine the PC, unique value of PC. Then PC is uniqueness. Then this is solution, of course. So if we can do this, then it's very good. But as I already mentioned that it's not easy. Of course, it's not easy to directly determine the unique, the correct solution. Then that's why we need another approach. And the second approach is unsafe theorem. In unsafe theorems, we use Vertex method, and we assume the mechanism, right? First, we assume the mechanism, and beyond the mechanism, we do the Vertex equation, develop the Vertex equation. Then we determine the P. Then P always greater than PC by using the Vertex method. Then this is upper bound solution. this solution is upper bound solution. If it's correct, then P equal to PC, but if it's not correct, then it's always a upper bound solution. And another word is unsafe solution for analysis. Okay, so if we use unsafe theorems, the solution is unsafe or upper bound solution or unsafe for solution for analysis. Okay. And the next theorem is the safe theorem. In safe theorem, we use equilibrium. And using the equilibrium beyond the assumption of the equilibrium set, then we can determine P. And the solution is lower solution. It means the solution is, if it's not correct, then the solution always smaller than the correct solution. Then we call this is lower bound solution. Lower bound solution. Or in another word, this solution is safe solution for analysis. Safe for analysis for solution for analysis. Okay, so this is safe theorem. Safe theorem. So now we have three different theorems: the uniqueness theorems, unsafe theorems, and safe theorems. But normally we usually use the unsafe and safe theorems in plastic analysis and design, and from now on we use the two last theorems. The next application of the virtual work equation is to determine upper and lower bound solution based on the limit theorems. I'm going to give you some example. Let's say two examples to illustrate the application of the virtual work method in determining the upper bound solution and lower bound solution. The first problem is analysis problems. Okay, analysis problem. Analysis means we are going to determine the load or load factor. Okay, the load or load factor. Okay, let's consider the frame. Photo frame like this. Let me first explain the frame. It is a frame A, and then here is B, and C, and D, and E, and F. This is value of the length of this part. For example, AB has a length of 5 unit, and BC has length of 5, CD is 10, and so on. Okay. Then this value is MP of the beam. So let's say MP of the beam, okay, MP of the beam equal to 3 times of MP at the column. So 7 to 720 unit. And this one is MP of the column. Okay, the MP of the column. So column and beams here has different section. Let's say the section of beam has 3 times of MP greater than the column. And the load is applied at the middle of the beam with 60 times of lambda, and the load at the middle of the column is 40 times of lambda, and lambda is load factor. Okay, lambda is load factor. Then our task now is to determine the upper bound solution and lower bound solution on the load factor lambda c. It means we have to determine the upper bound and lower bound of lambda c. And lambda c should be at between lower bound and upper bound. Okay? And we will not determine the exact solution of lambda c, but we determine the range of lambda c. The range of lambda c. That is our task now. And here we go. First, we use the assumed sway mechanism like this. Okay, sway mechanism like this. So this same mechanism, we assume the plastic moment occur at F, plastic hinge occur at F and at E, but the column because column has smaller section than the beam, and the plastic hinge also occur at D, at the middle of the beam. That is assumption mechanism, and we call this is sway mechanism. Not sway, but okay, a mechanism. And now we have displacement set and equilibrium set. Equilibrium set including the external force and internal force. So here's MP, and here here's MP of the beam. Okay, MP of the beam, and here's MP at the column. Remember, the MP at beam and MP at the column is different. Okay, so MP at beam is 720, and MP at beam is 240. Now we do the develop the vertical work equation. External work. External work is this external force multiplied by displacement. The displacement here is 5 theta because assumption rotation here is theta, and plus external force here multiplied by this displacement 10 theta. So we have this one. This is external force, external work. Okay, and internal work. What is internal work? This one, MP here multiplied by 2 theta. This one, MP here, MP of the column multiplied by 2 theta, and theta multiplied by MP of the column. Okay, then we can determine by solving this equation. We have lambda equal to 2.7. That is, so now we don't know if this one is correct solution or upper bound solution. If it's not correct, then it's upper bound solution, right? We do a moment check to unknown. We have two unknown. Unknown at MP, M at C, we don't know. And moment at B, we don't know. We have to check. And the condition is MP and MB. Moment at B should be smaller than this one. This one, okay? And moment at C. Moment at C also should be smaller than this one. This one. because we use small value at the connection, and the more value here, this connection is the moment of the column. Okay, so let's say MB and MC should be smaller than 240. Okay, here we go. Check moment at C. We check moment at C first. For moment at C, we assume the equilibrium set for the beam only. Okay, for the beam, because for the beam then we can determine MC. Then it's enough. We don't need to consider the column for MC. I already explained this application of the virtual work in moment check. Then this is magic method, right? So we just assume the equilibrium, the mechanism. So let's say mechanism here, this is MP and this is MP, then it's collapse. That is mechanism. We call this beam mechanism. With beam mechanism, we have equilibrium set like this, and we determine MC. And with this assumption, we have geometry set like this. Okay, geometry set like this. It is beam mechanism. Okay, beam mechanism. Now we have equilibrium set and geometry set, or displacement set. Okay, displacement set corresponding to this. Okay, sorry, let me explain again. Some confused thing. I think I need to explain again. So let's say, because we assume this mechanism, then we can easy to determine the moment diagram. Okay, so let's say moment diagram is like this, and here, and here, and we don't know here. Maybe like this. Okay, maybe like this. Moment here is 720. Moment here is 240, and moment here 240. We don't know moment here, and we don't know moment here. But first we consider the beam only. Okay, then this one is here. Okay, this one is here for the beam, and we assume this mechanism. We assume the displacement set and beam mechanism, using beam mechanism. And by using this equilibrium set and geometry set, we develop the virtual work equation. It is internal work. Okay, internal work. MC multiplied by minus theta, and MP of the beam here multiplied by plus 2 theta here, and moment here MP of the column, and E is minus multiplied by rotation here is minus theta. Okay, that is internal force. Then external force is what? This one multiplied by this displacement tan theta. Okay, so by solving this equation, we have MC equal to 60. Then 60 MC smaller than MP. Smaller than MP of the column, then good. Okay. Now we do the moment check at B. Previous one is for C, and now is B. This is moment diagram of the column ABC. Okay, moment diagram of the column ABC. We already determined MC equal to plus 60. And now we have to check M at B. Okay, M at B. We don't know M at B. For doing the moment check of the column, we can assume the column mechanism only. Only consider the column mechanism like this, and we have displacement set corresponding to the mechanism at the column. Okay, so again we can assume the mechanism independently compared to the whole structure to do the moment check. Okay, that is like magic method, magic application of the Vertex work. Okay, now we have equilibrium set and this displacement set. Then we can develop the Vertex work equation. Again, what is internal work? Internal work equal to MC multiplied by minus theta here, and MB multiplied by plus 2 theta here. That is internal work. How about external work? External work is this one, the force multiplied by the distance here. It is 5 theta. 5 theta. Okay. Then, by solving this equation, you can easily to determine MB. MB equal to 300. So what happened? 300 is greater than MP. Okay? MB is greater than MP. So it's not good. So it means the lambda or the load factor 2.7 is upper bound solution. It's not correct solution, right? Then what next? Now if we scale down the whole moment diagram by dividing this one to this one, okay, MP by MB, then we have equal to 2.8. So we have to reduce this value to MP of the column to 240. Then the scale down factor is 0.8. Then now we also scale down the load factor by 0.8. And what happened? Now lambda now equal to 2.7 multiplied by this factor 0.8 equal to 2.60. 16. Okay, and this is lower bound solution. Okay, lambda equal to 2.16. It is lower bound solution. And now we have lambda c greater than 2.16 and smaller than 2.7. This is range of the lambda c, and it's always lambda c or load factor always in this range greater than 2.16 and 2.7. Okay, so that is the solution of analysis problem. We don't know exactly At this time, we don't know exactly, but we know the range of the load factor.